All right, so we were talking about the age of the Earth and how we know, well, not just the age of the Earth, the age of the Moon, the age of Mars, the age of um, you know other objects in the solar system. Uh, for example, comets and asteroids. Sometimes they will uh, you know crash into the Earth, or at least parts of them, and we can analyze the the radioactive elements that we find in those objects. And we always get the same number, right? That's the key thing, right? No matter what type of radioactive, it has to be something with a long half life. I mentioned potassium 40. There's also, of course, uranium 238, which becomes lead 206. And every single time you do this, you get the same age of 4.5 billion years. Right, so that is, overwhelmingly convincing that the age of the Earth and the rest of the solar system is 4.5 billion years. Actually, the Moon is just slightly younger than that. The Moon formed a little after the Earth. We'll get into that later. All right, so now let's turn back to the Earth itself, and we'll start exploring what's going on under our feet. Of course, we have the crust. We mentioned that before. That's the land that we're on. And also there's crust underneath the oceans as well. All right, you go down a little further than the crust. Um, let's say um, about 40 kilometers or so down, in towards the center of the Earth, and then the crust is different, uh, different depth around the world, but you get down to around 40 kilometers or even 50 kilometers or so, and now you're completely in what's called the mantle. Within the mantle, of course, there is rock. Uh, it's kind of like you can almost think of it as a plastic. It's a very, very dense plastic. I mean, we think of it as being solid, but it's solid, and yet it can move as well. Right? That's a strange idea. It really has to do with the heat that's in the core. So underneath the mantle is the core of the Earth, the center of the Earth, and of course there's two cores. There's the outer liquid core and then the inner solid core, and both the cores are made of primarily iron and nickel. All right, so what happens is you have hot material that rises, and then when it gets closer to the crust, it will begin to cool off. And so hot material will rise, because it's less dense. Just like a hot air balloon, right? If you put hot air into a balloon, the air is less dense than the surrounding air of the atmosphere, and so the hot air balloon will rise. Not right away, but when it becomes less dense than the surrounding air. And the same thing goes with this. Well, yeah, it is. I'll say solid, but it's really more of a kind of a very thick plastic. Um, I mean, it's not plastic in this. It's not made of plastic material, but it has a certain plastic. Um, um, Properties, very, very similar to plastic. The mantle. All right, so the hot material physically rises and begins to cool off as it gets towards the crust, and then as it cools off, it gets more dense, and then will start to move downward. So that motion of hot material rising and cool material falling, and so these circular paths is called convection. So convection is a method, a mode in which heat can travel. So heat travels by convection, also conduction and radiation. All right, so those are the only three ways that heat can travel from one place to another. All right, so convection is when the hot material physically moves from one place to another. All right, with conduction, which is a different story. Like that's like when you heat a piece of metal, and eventually, if it was like a bar of metal, if you heat one end of it, eventually the other end will get hot because the metal just basically passes that heat, which is really just vibrations. It'll pass that vibration from molecule to molecule without the molecules physically moving or going anywhere. They just vibrate back and forth. This, of course, is convection. Convection is when the hot material physically moves. It moves from location to location. All right. So that, and then of course radiation is when that's a totally different thing. That would be like light. Light is considered electromagnetic radiation, or gamma rays, or infrared light. They're all considered forms of electromagnetic radiation, and they travel, of course, at the speed of light. Radar beams do this. Radar signals do this as well. So does radio. So does ultraviolet. All these things that we will be talking about when we start talking about the atmosphere. At any rate, that doesn't need a medium to travel. A medium is like what the heat travels through. So like, for example, convection and conduction actually need physical connections, right, between where the high temperature source is and the low temperature source. With radiation, right, when heat travels through by radiation, there doesn't have to be a physical connection. In fact, there usually isn't a physical connection. And so radiation can cross the vacuum of space. And so that's an important idea. And that's in fact how we get heat from the sun, right? The sun, there's no physical connection between us and the sun. For the most part, there's not. And there are streaming particles that leave the sun, but that's generally not what I'm talking about. The heat that we feel from the sun, for the most part, is just in the form of radiation that crosses the vacuum of space. All right. So anyhow, getting back to the Earth, right? So within the Earth, we have this hot material rising and then falling, and that's happening all over the Earth, and it's been happening since the beginning of the Earth. Remember, the formation of the Earth really is what causes it originally caused the entire Earth to be molten, liquid, and so that that the more dense materials ended up at the core. But of course, since then, large parts of the Earth, including the mantle and the crust, have solidified, right? So now this is the kind of thing that where heat has to travel from the center of the Earth towards the crust, there is you might think, okay, well, the Earth has been around for 4.5 billion years. Why hasn't all that heat escaped? And it really has to do with the shape of the Earth, right? The Earth, the fact that we're a sphere, really holds on to that heat very, very well. And the other thing, of course, and I've mentioned this before, is there are radioactive particles, radioactive substances inside of the Earth. Huge deposits of uranium, for example. Uranium is probably the most common radioactive isotope. And so, you find all this uranium. We find it on the crust, of course. We use that all the time to build, to power our nuclear power plants. But there's a lot of uranium within the Earth as well. And when that uranium is undergoing, radioactive decay, just like the uranium, in our nuclear power plants that we've mined from the crust. And so when the radioactive material inside of the Earth is undergoing radioactive decay, it releases heat as well. So there's a source of heat that's still around within the Earth, right? That's the radioactive. That's part of what the radioactive process does, is it releases heat. So there's, in other words, there's a replenishment of heat that's going on as long as there's radioactive material. And when you're talking about uranium-238, it has a half-life of 4.5 billion years. So since the Earth has been around for 4.5 billion years, half the uranium-238 is gone. It's turned into lead. Lead-206 in fact, but there's still half of that original uranium-238 around, and so it's still undergoing decay, and as it does so, it's still releasing heat. All right, now of course that's not always going to be the case, but you're talking about billions of years into the future. All right, so anyhow, so this is just showing you an example of convection, right? The hot material rises, it cools off, and it falls. It's exactly the same thing that happens if you have a pan of boiling water on your stove. The hot material rises, it cools off, and you can see this when the water begins to bubble, and of course when steam starts coming off. That indicates that the water's boiling, right? Maybe you're going to make some pasta or something like that. All right. Now, when this happens, of course, that affects the crust. When this happens, being when the hot material rises, and then cools off and then falls, sometimes that will affect the crust in a very visible way. And one way that we talk about is what's called rifting. Right? So there's two things basically that we're going to talk about here: rifting and subduction. All right. So rifting is when the Earth's crust. Remember, this is the top layer of the Earth. Separates. So hot material rises up. And it rises up so far that the material, this mantle material will rise up and reach the crust, and basically it pushes the crust apart, and becomes new crust in and of itself. By the way, it becomes new crust. So as it rises here, it'll go to the right and to the left. In fact, this is well known. This is a region of the Earth between North and South America and Europe and Africa. Right, it's called the Mid-Atlantic Ridge. It goes right through the middle of the Atlantic, and it has been spreading, since, well, let's see, it's been spreading for about 250 million years, and that's actually what's formed the Atlantic. There was a time when the continents were connected, and since they've been spreading ever since.